Yeah. All right. So yeah, welcome back everyone to this got some amazing turnout this week. Whopping two people here, but thanks for joining us today. Um so we're looking at, op amps and additional analysis techniques. And so it's additional in the sense that you probably won't come across these techniques too often in practice, but they're, typically taught because they have a lot of good historical background to why these things emerge. And they do come into play for very special situations, and we'll kind of talk about that as we get to them. And I'm noticing now that I misspelled amplifiers here. Off to a good start. All right. So op amps. These are just like the learning goals from, chapter five, or sorry, chapter four and five that we're covering. Right. So four is on the op amps and five is on the additional analysis techniques. So we're kind of just learning how to model the op amp and kind of looking at circuits that employ op amps. And I didn't really get to this like last learning goal. It kind of comes in, more practice when you actually look at circuits that are kind of useful, but it's hard to, reach all these learning goals in the little limited time that we have here. But it's kind of good to get at least the introduction to them, I think. So op amps are pretty complex, and this is kind of a picture of a discrete op amp, just made from different parts. I got this picture from Wikipedia. It's not actually from the textbook, but I think it does a good job of showing what an op amp looks like. And typically, you'll see op amps packaged in some kind of silicon, and then has some case, some black case around it. But here is what the internal structure of kind of a basic op amp looks like if you were to build one just from discrete parts. And so you can kind of see some resistors, there's some diodes in here, and a bunch of transistors. These little metal can things are transistors. So obviously they're very complex, and we can't necessarily analyze them with the tools that we have so far, but we can actually model them in a way that's a little bit simpler. And so this is typically what the op amp looks like in a circuit diagram, right? It's just got these one, two, three, four, five different pins here. Um, a lot more simple than drawing out a circuit that has all these parts in it. Um, and so the op amp basically works as a voltage amplifier. It's historically named operational amplifier because it's been used to actually do a lot more than just act as a voltage amplifier. Like it's been designed to make adders or multiplier, differentiator, subtractor, all these kind of different operations, right? These mathematical operations that we're kind of used to. And so they amplify an input signal using power from some kind of voltage source. And so you'll see in the circuit diagram, there are these two input, right? The non-inverting input and the inverting input. And you've got two power supply pins, this positive power supply and this negative power supply. So usually when you're powering the op amp, you'll see what's either called a dual rail supply, where there's actually literally a positive voltage source and a negative voltage source, or you might see single rail, where you'll have just a positive voltage source and ground. And so I didn't put that there. That's a little bit outside of the scope of this, but that's just something to keep in mind. Um, and so aside from the input pins and the supply pin, the power supply pins, we have an output pin. And again, we're amplifying the input signal using power from our voltage source, and it outputs onto this, output pin here. And so it's related by this expression here where the output voltage is equal to the gain, right? This is the gain of the op amp. And then the difference between the in non-inverting minus the inverting inputs. And so you'll notice that when the non-inverting input increases, so does the output voltage, right? And so that's why we call it the non-inverting input. And there's similar logic follows for the inverting input, right? If we increase the inverting input, the output actually decreases, hence inverting. And so yeah, again, the symbol here and all the pin names I pulled from Wikipedia, and then just like the learning objective that it ties back to is just learning how to model it. And I'm having all kinds of typos here. Sorry about that. So the output of the op amp is always going to operate between the supply voltages, right? So for example, if we have our positive supply to be 3 volts and our negative supply to be minus 3 volts, then the maximum output voltage is positive 3 volts and the minimum output voltage is minus 3 volts. And so whenever it's operating whenever it's kind of reached this extreme value, it's said to be saturated or operating in a saturation region. So here, kind of in this diagram, I've got an example of negative saturation is this bottom left here, where you can kind of see the output voltage is just kind of clipped off, right? It stays the same no matter how much it changes on the input. And then on the other end of the spectrum, we've got positive saturation where it's just clipping, in the positive region there. And then in between the two saturation regions, we've got this linear region where if we increase the inverting input a little bit, right, that's going to lead to an increase in the output. And then if we, decrease the non-inverting or if we increase the inverting, it's going to go down. Um, and so that's the linear region, kind of this output voltage curve, really. Um, so the ideal op amp has two main assumptions. These are kind of like the big assumptions that really help us with our analysis. And so the first one is that no current flows through the input. So if I'm looking at the current going into this op amp, it's going to be zero, ideally. And then the voltage at the inverting input is going to be equal to the non-inverting. So these voltages we call it a virtual short. We don't actually connect these two inputs together, in a typical circuit, but just keep in mind that they are virtually shorted together. So it's these two assumptions that really, make the analysis easy and kind of allows us to not have to deal with all of the complicated circuitry that's going on inside of the op amp. Um, so as a first example, we usually consider this unity gain buffer. So I've drawn it down here in the bottom right. But basically, we've got an input source connected to the non-inverting input, right? So here's my voltage source. I've connected it to the non-inverting input there. And then I've got the output voltage and I'm feeding it back into the inverting input, right? So there's that connection there. Um, and so by the input voltage assumption, right, this is the assumption, the non-inverting input is equal to the inverting input. And so this implies that the input voltage is equal to the output voltage, right? Because if that voltage right here is the same as that voltage right here, and these are tied directly together, then input is equal to the output. Next, by the input current assumption, we have, the current into the op amp is equal to the current out of the op amp, or into the inverting, the current, into either of the input pins is equal to zero, basically. So what we've done here is we've created a circuit that follows the input voltage, right? That's why it's called the voltage follower, or kind of this unity gain buffer, because there's a gain of one, right? It's the input is equal to the output. Um, and more importantly, this input voltage source doesn't really need to supply any current, right? This output voltage is just kind of tracking the input voltage. And so that can be helpful when we're trying to drive some kind of circuit downstream. And maybe this isn't like the most perfect voltage source in the world that we're inputting, that we're trying to track here. So that can be useful because, as you know, if I attach a resistor at this output, it's going to suddenly start to want to draw current. And if that resistor gets big enough, that could maybe um, mess up this input voltage source that we've got here, right? Maybe try to bring it down a little bit. Um, anyways, so yeah, that's kind of this unity gain buffer. And I think, yeah, the next part is really just talking about this problem solving strategy. So basically, we're just using that ideal op amp models where we're looking at the input currents are always going to be zero, and the voltage at the non-inverting terminal is always going to be equal to the voltage at the inverting terminal. And then we kind of just apply this nodal analysis that we talked about last week to the resulting circuit, and then we just solve the nodal equations and figure out the output voltage. So it's pretty straightforward. I think op amps aren't too difficult. They can be kind of scary at first because it's a completely new circuit symbol with a bunch of more almost foreign rules. But once you get the hang of it, they're not too bad. Um, and so with that, unless there are any questions, we'll jump over to some of these example problems. So feel free to chime in if anyone has any questions here. Otherwise, I'll connect up my iPad here.
Uh, I had a question, RJ.
Yeah, what's up?
So can you maybe explain again how there's no current going through the input nodes and like how that works or like why
Yeah,
that
I
is?
mean, so I can't I mean, so this is it's a simplification of this mess here.
Hmm.
Um so it's kind of hard to really go into detail without like looking at the innards of this circuit. But the general idea is that I think one assumption that, maybe I left out a little bit is that there's infinite input resistance or impedance, we call it, right?
Mm,
So um, basically what that means is that there's a giant resistor, in the path from the input to the output.
okay.
Um, and you could just imagine that really if it helps you.
Okay. Yeah, that
Um,
does help. Yeah.
but yeah, so I mean these are just kind of the rules that we kind of make up for, this ideal op amp. And um yeah, again, like without going into great detail on the operation of electronics, it's hard to explain some of these assumptions really.
All
And
right.
and quite frankly, I haven't studied enough to actually give a full answer on that. It is an interesting topic and a good question. Um, but it's not too necessary actually. You
Yeah.
can pretty easily get around circuit analysis without having to know these things, which is kind of nice.
Mm. All right.
Yeah.
Thanks.
Yeah. So let me see here. Oh, all right. That should be sharing now. And let me just pull up these examples. Sorry, taking a bit here. So we want example 4.1. So this example is not necessarily like a circuit analysis example. We're just kind of looking at the input and output characteristics um, of this op amp circuit, I guess, that they've just plotted really. So the input is looking something like this, and then the corresponding output circuit um, looking like this, where it gets up to here and it clips. and then it goes up to here, and then also clips, something like that. And so it's just kind of asking if the op amp circuit, right? So we're looking at where the op amp is in linear region versus saturation region. So this is the time in milliseconds, and then this is the voltage axis here. So here I've got in black the output voltage, and then in red again is our input voltage. And so one thing that they have here also is that the input is going up to about 2 volts, and the output, it's kind of hard to tell here, but kind of looks like 3.3 volts up here. So they've got 3.3 volts. So, clearly they've got a 3.3 volt supply. It's going up to minus 3.3 volts here. And so as we had discussed before, the linear region is where like a change in the input corresponds to a change in the output. And so we can kind of see that right here. Let me just highlight it or something. Right, so all the way up to about here is where we're in a linear region. Um, and so they've marked that down as 1 volt, I guess. So this is about 1 volt, and I guess I drew that pretty well actually. So at 1 volt, we can see that the op amp has actually saturated um, to 3.3 volts on the output. And so this way we can actually determine the gain of the op amp, right? So if the Vin of 1 volt gives you V out of 3.3 volts, then we have our gain. And so the gain in general is given by the output divided by the input. We're looking at the ratio of how much of the output is getting to that input, really. And so that gain is going to be 3.3 volts over 1 volt, which is just 3.3. Right. So anywhere before we've hit this 3.3 volts is where we're in a linear region, right? And then we're in saturation um, whenever the input is above the 1 volt here. So we're in saturation all the way up to um, well, I guess so it's going up and then it's also decreasing. So whenever we're above 1 volt, we're in saturation basically on the input. So hopefully that's clear to you guys. I know this is not the greatest drawing in the world, but I think it gets the point across at least. Oh, I left a lot of space there. So if there aren't any questions, we'll move on to this next example, 4.3, where we actually kind of look at an op-amp circuit. Um,
Can you give an example of how like the input voltage would kind of change? Like is the non-inverting one decreasing? Kind of like what are we seeing in the red?
yeah, I mean, so this would be, that's a good question. Um, Here you can imagine, right, whenever we have a zero crossing, that's kind of where, right, because the original equation that we were looking at is, the output is related to the gain times the non-inverting minus the inverting. So at any zero crossing, you can imagine um, the inverting and the non-inverting are literally equal to each other, right? Because then the output voltage is zero. Whenever we're increasing, you can imagine the inverting to be increasing or the non-inverting to be increasing, right? You got to hold one the same. Um, but yeah, and then likewise, whenever we're decreasing, either the inverting is increasing or the non-inverting is decreasing, if that makes sense. Yeah. Okay, good. Um, but yeah. All right. So next we're looking at this little circuit here. So actually got an op amp now, and we're taking some input here, and we're feeding back the output through a resistor. This is called a feedback resistor. They've labeled it RF, and I guess this is maybe some kind of input resistance, um, RI. And we're trying to determine the gain of the op amp here. And so as you'll recall, um, the gain, sorry, let me just label this. So this is the output voltage. The gain, oops, is typically given as the ratio of the output to the input. Um, and without looking at the solution here, I'm going to try to do this just to show you guys how I would do it at least. So we know that the input voltage, right, the non-inverting is equal to the inverting. So I've actually got Vn right here, right? And so if I know that, then I know, the voltage right here, and I can actually determine the current that's going through this RF, this feedback resistance here. Um, and so if I define the currents, just flowing down to ground like so, and you'll recall that no current is going into the inputs of the op amp there. So I've got VO, um, right, I've got VO here, so then minus VN over RF, right? So that's that current, this current here through RF. And then I know that the current through RI is going to be VN over RI. And so that's going to be equal to zero, right? Just by KCL. So if I look at KCL at this red node here, the only currents that I really have is maybe I'll call this IF and I'll call this I guess. And so there's no current this way, so I minus is zero. So I don't even need to consider that in my analysis here. Right, and so by KCL, I have my IF minus II is equal to zero, and I've written it out here. And again, so our goal is to figure out the gain. So what we'll want to do is probably separate out these two voltages. So, from this first expression, I have a 1 over RF term for my V out, and then I've got a minus 1 over RF for my V in, and then I've got a minus 1 over RI, um, contribution to my Vn there. And so that'll be equal to 0. And so if I, let's see how I want to do this here. So if I move Vn over, then I've got, oops, then I've got Vn, right? So these minuses just turn to pluses, Rf plus 1 over Ri. And then I can just multiply by Rf and then divide by Vn to get Vo over Vn is equal to Rf times 1 over Rf plus 1 over Ri. And so if I simplify that a little bit, I got 1 plus Rf over Ri. And so this is the gain of, oops, this op amp network that we just had up here. And so you'll recognize this as a non-inverting op amp, right? Because we're feeding our signal into the non-inverting input. And then the output is actually feeding back into this inverting input. So this is the basic non-inverting op amp. Um, so are there any questions on that? Hopefully that was somewhat easy to follow. Um, nope. All right, cool. So
Did you have to tie it to ground? Like,
yeah, so that was just part of the circuit that they gave us here. But it kind of depends on what. Yeah, I mean, so for the typical non-inverting op amp configuration, yeah, you would consider that to be kind of like ground, right? And I guess I forgot to draw this as well. So it's also like a single supply. Their negative source here is tied to ground as well. Um, but yeah, no, that's an interesting question because you know, we always talk about ground, but what really is ground? And that turns out to be a really difficult question sometimes. Ground is really just a reference point where we define, to be the zero potential for the sake of analysis, but that's hardly ever the case. Um, so I mean, in this case, yeah, we just defined it to be ground there. I don't know how else to explain that, honestly. Um, But yeah, if there aren't any other questions, we'll go on.
Also,
Yeah.
um, not re in relation to the ground, but like in relation to the voltage supply.
Uh,
Like if you're actually like using an op amp or whatever, like in a circuit, would that just be like hook up to a power supply or something like that?
yeah,
Like,
and
yeah, I'm not.
right, so it can actually get kind of difficult
So
um making these kind of circuits, right? Because you need some kind of negative supply, and that's not necessarily a trivial thing to do. Um, but yeah, so whenever you're building this up in the lab, yeah, you'll probably just use a bench supply, or when you actually get to build one that's kind of just standalone. Oftentimes you'll use a battery or something. Um, and so again, it can kind of get tricky to create a negative voltage source from a battery, but one obvious way to do that is kind of just to reference, like maybe you have this is like an aside, but maybe you have like a battery, right, and it's giving some positive voltage this way, right? Maybe this is a 9-volt battery. What you can do is you can call this ground, right? And then you can just hook up another battery, right, in series, oops, kind of like the same way. And if this is 9 volts, then this is, the voltage over here with respect to ground is actually minus 9 volts. And then this is going to be plus 9 volts. And so that's one way you could do it. But yeah, that's a good question because, that is something that arises like in E409. Like how do you actually create this dual supply? And it is somewhat difficult if you only have one battery. All right, so feel free to jump in if you have any more. I'm just gonna chug along here. All right, so next we're looking at another op amp circuit. Um, so this is just really to get more practice with them. There's nothing special about this circuit. So we've got R1 going into the inverting input, R2 feeding back from the output, and this is the output. I guess they've just drawn in a single supply, so grounding the negative supply there. They've got R3 going into the non-inverting input from, so they've actually got two sources here. So V1 is going into the non-inverting, or sorry, the inverting, and V2 is going into the non-inverting. And then they've got R4 tying from the non-inverting back down to ground. Um, and again, we're just looking for this output voltage. So without looking at the solution again, hopefully I can do this. This is kind of good practice for me. So if I when I look at this circuit, I see that I don't necessarily know any of the input voltages to the op amp. But what I do know is that no current goes this way, so it's pretty easy to figure out the voltage there. And so that voltage is just a voltage divider. So this V plus is going to be V2, right, times our R4 divided by R3 plus R4. Um, and that's actually going to be also our inverting input V minus, right? And so with that information, I can now start to move my analysis over here, right? And I've got current going that way, and maybe current feeding back through there. Um, Obviously, one of those are going to need to be negative. Actually, not sure which one in this case, but we'll find out here. So if I call this I1 and I call this I2, then the way I've written it here is I1 plus I2 is equal to 0 somehow. Um, and, the way I've drawn this, I1 is going to be V1 minus V minus over R1. And then I2 is going to be V out minus V minus over R2. And so this will sum to 0. And again, we're looking for an expression for the output voltage. So we'll want to kind of separate out these terms to make life a little bit easier here. Oops. Right, and so what I'll do next is I'll move everything over and multiply by R2. So I've got VO is going to be equal to R2 times my V1, times 1 over R1. And actually, since I'm moving it over, this is going to be minus. So that'll be minus 1 over R1. And then this will be V. Oh, wait, what have I done here? This is supposed to be V minus plus V minus. And then since I've moved everything over, these are going to be adding. And there we have it. That is an expression for the output voltage. And then obviously, V minus is, I've figured out what that is in terms of the input voltage up here. So you could expand that out if you wanted to here. And maybe we'll do that just for the sake of doing so here. So V1 minus 1 over R1 plus V2 times R4 over R3 plus R4. And then this is going to be times 1 over R1 plus 1 over R2. Um, and that'll be that. So let me double check to see if we've kind of arrived at the same conclusion here. Kind of looks like they've got a much simpler expression. So I might need to go back and see what that's all about. But actually, yeah, I do have. Okay, so yeah, I've got their same expression before that. So this is right. And then they make this note that if R4 is equal to R2 and R3 is equal to R1, then the expression reduces to the output voltage is equal to R2 divided by R1 times V2 minus V1. And this is the expression for what's called a differential amplifier. And it's called differential amplifier in the sense that it's amplifying the difference between the two input voltages, right? I've got V2 minus V1, and then I'm just scaling it up by some constant here. So in any case, it's proportion. The output is proportional to the difference in the input voltages here. So there you have it. Um, any questions on that, I guess? No.
Can I ask how you got the equation under the current plus current equation?
This I1 plus I2 is equal to 0.
Oh yeah, right below that. What's
Yeah, so um, I've got I1 here, right? And so current is in general voltage over resistance. The voltage is going to be V1 minus V minus, right? Because I've got V minus here, right? And since current's always going from the higher potential to the lower potential, right? So I've got the difference V1 minus V minus. And then the resistance, that is occurring between those two potentials is R1. And so that's I1. And the same thing follows for I2. I've got
okay?
V out, right? VO here. And I'm going from VO to V minus through R2. So that's where my I2 comes from. Good?
Yes.
Okay, cool.
Yeah. Yeah.
All right. Um, cool. So that is kind of all the example problems for this
RJ,
chapter. Yeah, what's up?
I also noticed that you had like a ground um like symbol like hooked up to the positive power supply. Is that because the negative power supply would be like negative voltage?
Oh, sorry. Yeah, it's kind of weird how they drew it, but whenever they've got the lower
Just leave that there.
thing,
Sorry
that's
for
the
my
negative supply
problems.
usually.
Oh,
Um,
okay.
But I mean, there's nothing really stopping you from, yeah, connecting the positive supply to ground and just the negative supply to negative source.
Okay.
Um, they've just drawn it like that for some reason. Yeah. All right, cool. So I guess I got 10 minutes here. So maybe we'll just go through some of the slides here and kind of talk at a high level about some of these other additional techniques. You guys can see the slideshow right now? Yeah, okay. So additional analysis techniques. So we're looking at concepts of linearity and equivalence, and then using the superposition principle, looking at Thevenin equivalent circuits, and then Norton equivalent, and just the maximum power transfer theorem. Um, so again, these are additional techniques that I actually haven't really used in practice, but for historical reasons, they're taught at the undergraduate level, really. But they're good to be aware of in case you ever do see them come up in some kind of application note or something. Well, I mean, everything beyond the equivalent circuits that we're kind of just going over here. So these are pretty important. So looking at equivalences for resistive networks, right? We've kind of seen this in practice a lot, but whenever you have resistance in series, those are going to be additive, right? It's like if I have two roadblocks, right, in the way, it's going to be twice as hard to get through. If I've got two paths with different roadblocks, right, it's going to be the same as kind of one with a little bit less. So conductance in parallel is additive, but that's the same as saying that if we have two resistances in parallel, we can take the product over the sum to get the equivalent. And so I've drawn that out here very professionally in MS Paint. Um, some other useful equivalences kind of occur for sources. So here we got voltage sources. So whenever they are occurring in series, these are going to be additive. And so you can see um, these are actually drawn in different directions, right? I've got the V2. If I were walking from this bottom node up, it's coming out of the negative, and if I'm going through V1, it's coming out of the positive, right in this path to this guy. And so we can replace that with a single voltage source by just adding them up. And so in this case, I'm considering V1 to be positive, and then V2, since it's hooked up in the opposite polarity, to be negative. And then likewise, current sources in parallel are additive. So in this case, I've got two current sources in parallel. One is going upwards, the other one's going down. Um, and so if I were to look at the equivalent of just one source going upwards, then I've got the one that's pointing in the same direction is positive. The one going the other way is negative, so I can just add them up in that sense, and that'll be an equivalent. Um, So another useful technique is this idea of superposition. So whenever we have a linear circuit, we can use superposition principle to look at how each source impacts the circuit. Um, so here, I've got a circuit and it's linear because it's just got resistors and sources. Um, and I've zeroed out the voltage source. And whenever we zero out a voltage source, that's the same as replacing it with a short, right? Because whenever we have a short, there's no voltage drop across it. And then likewise, if I zero out the current source, I replace it with an open because there will be no current flowing through an open, right? I just completely rip it out of the circuit there. And so if I add up, if I were to maybe I'm interested in figuring out the voltage across this resistor right on the left here. Well, I could analyze these two circuits separately, solve for the voltage drop across that guy in both of these circuits, and then add that up, and then I'll get, the voltage across this circuit here, which is a little bit more complex, right? Um, so that's, one technique that comes up once in a blue moon maybe, but it's good to be aware of it, I guess. So here's, just a simple problem solving strategy for superposition. So basically, we just create a circuit for each of the independent sources, um, however many independent sources that we have, right? Turning off all the other sources. And again, to turn them off, we replace the voltage sources with a short and the current sources with an open. Um, then you solve the circuit for whatever you're looking for, and then you add up the contributions, and you've got your answer to whatever it is you're trying to solve. So I'm not going to go through these examples, in the interest of time. But it's good to, if you have some chance to read through them, it could be nice. Let's look at them, I guess. So moving on to Thevenin's theorem. This is another theorem that I've never personally seen in practice, but it's good to know. So in any case, you can reduce any network, and you can replace it with just an independent voltage source in series with a resistor. Um, and so it's kind of related to the open circuit voltage minus some Thevenin resistance, right? And then you can figure out what the current is just by, if you know whatever the resistance of the load is, then you can determine that really. Um, so, this is useful when you have really, really complicated circuits, like maybe, one of the examples I think is something like this, where we got like a source and you got like a resistor here, resistor there, maybe like another source here or something, right? Resistor, bunch of bunch of these resistors all over the place, and we're looking for like what happens across this guy, right? And that's kind of difficult to determine right off the bat here, but if we kind of reduce this whole mess into just a voltage source with a resistor, then it can make our life a lot easier. And so that's one of the benefits of Thevenin's theorem. And it can be especially useful if you're interested in one very specific part of your circuit, and um, it can help to just reduce everything and just figure out what's happening in that one part. Um, so Norton's theorem it's basically a restatement of Thevenin's, but instead of a voltage source in series with a a voltage source in series with the Thevenin resistance, you've got the a current source in parallel with the Thevenin resistance here. Um, and without going into too much detail, kind of just jumping into the problem solving strategy for this guy, these theorems. So basically what you'll want to do is you'll need to know what part of your circuit is, what's called the load, right? Where we're trying to figure out, basically we remove that part of the circuit and we start off by figuring out the voltage across that circuit, just due to whatever else is going on. Um, and I think maybe since we've got a little bit of time, maybe I'll jump through one of these examples because it could be helpful. I think superposition is pretty easy and straightforward, but this can be a little bit challenging. Um, and so once you've figured out the open circuit voltage, right, across that load, then you want to determine the Thevenin equivalent resistance. Um, and so this is a little bit more tricky because it depends on what kind of sources you have in your load, really. And I think the example we'll take a look at just has these independent sources. Um, so if there are only independent sources, basically all you do is zero them out, and then you determine the resistance that's seen by the load. And we'll look at what that looks like. Um, there are also these more advanced methods where, if there are only dependent sources, then you kind of supply a test source at the load, maybe like a 1 volt source or a 1 amp source. And then you determine if you apply a voltage source and you want to determine the current that's coming out of it or going into it, and then that'll give you the Thevenin resistance. And then if you apply, a current source, then you need to figure out the voltage across that current source. And, in any case, you can figure out the Thevenin resistance there. Um, and then if there are both independent and dependent sources, then you kind of need to short out the load and figure out the open circuit. Right, you've already figured out the open circuit voltage. You just need to determine the short circuit current, and the ratio between those two will give you the Thevenin resistance. As you know, that's just by Ohm's law, really. Um, and so once you've determined both of these, you then just kind of make your Thevenin equivalent circuit, and you can figure out whatever it is you need to with that circuit that you've got. So, oh, I guess the last thing is just maximum power transfer. So it can kind of be shown that whenever the Thevenin resistance, whenever the load resistance matches the Thevenin resistance, that's actually going to give you the maximum power transfer. And there's a derivation of that in the book that could be worthwhile. It's got a little bit of calculus. It's kind of just taking the derivative of, maybe we'll just walk through it here. So I could probably do this. So we got a voltage source. We've got some Thevenin resistance and some load resistance, right? And, by the voltage divider principle, this load voltage is going to be the source times the load resistance divided by, the sum of the Thevenin resistance and the load resistance, right? And so we know that voltage is related to power. P is I times V. If we know that V is that, um, if we know that I is V over R, then voltage is related to power as V squared over R, right? And that's by Ohm's law, this V divided by R. So we've got V squared over R. So basically we've got P is equal to this whole thing, Vs squared times RL over RL plus R Thevenin, right? And this guy is squared. And again, we're looking for the power across the load. So this is going to be divided by RL. So if we take 1 by RL. And so from calculus, you know that if you take the derivative of something, and then in this case, I think we're taking the derivative with respect to RL, and you figure out that the derivative is equal to 0, right? You find the points where the derivative is equal to 0. Um, that's by the extreme value theorem, you can determine that that's maximum or a minimum. This is like a strictly increasing function, so this will be a maximum, or sorry, it'll be, concave up like that. So that'll be a maximum. And, you can you take this derivative, solve it for, set it equal to 0, and you can find that RL will be equal to RTH. And, you can read about that in the book if it's unclear. But, that's an interesting takeaway from the Thevenin equivalent circuit. And I think it comes up a lot in maybe like RF situations where you're actually trying to maximize the amount of power that's getting to some kind of load, in terms of like resistive networks or some kind of impedance of whatever network that you're designing here. So yeah, it's kind of neat. Um, all right, cool. So then we'll just jump through maybe one example here. But I'm happy to take any questions if there are any again. I know that maximum power transfer was very quickly done, but hopefully that made sense. All right. So let's see. Do you guys see that the iPad screen again? Yeah, all right. Stick. Okay, so let's jump over and I think we're gonna do 5.9. Yeah, okay. So 5.9. Let me just pull it up on my computer here too. Oh boy. All right, 5.9. So, oh boy, picked one with, wait a second, this one with a dependent source. Let's do maybe 5.7, because the dependent source can be a little bit more tricky. All right, so we're doing 5.7, and we've got this circuit. It's got a voltage source, it's got a bunch of resistors, current source, a couple more resistors. So this is a 3K, this is a 2K, this is a 6K, 4K, 8K, and they're calling this the output. The 12-volt source, and this is a 2 milliamp source. And I really hate when they throw in like numerical examples because I like to do things more algebraically, and having to write all these numbers kind of makes everything a little bit more difficult. But anyways, so we'll start off by, again, just kind of looking at the open circuit voltage, and they've already kind of removed um, the load really. So we're going to take a look at, well, I guess this 8K is kind of like the load. So make sure that they did that. Yeah, so they've done that. So we're going to start off by um, sorry, maybe I should have reviewed this one beforehand. I'm not really sure which way they're taking this. A little confusing to me. But yeah, actually we're kind of out of time here anyway, so I don't want to take keep you guys here for too long. But maybe we can kind of pick up next week with